Good morning, everyone. I want to welcome you to another multivariate statistics class. Of course, we got a lot to do today, being the last day before spring break. I believe next week is spring break, right? Okay. So, like I said today, we got a lot to do. I remember I stopped here Wednesday. So I'm going to start from where we stop. On Wednesday, I introduce you to, multiple vectors, inference on, particularly two vectors. And of course, I walk you through how to conduct statistical inference on that. So when I mean statistical inference, constructing confidence interval and testing hypothesis. So, but the approach that we use in constructing confidence interval and hypothesis testing, assume that the two groups having the same covariance structure. I'm going to say that again. The approach that was used on Wednesday assumed that the two groups are assuming, they have the same covariance structure. And so what happened when the covariance structures are not the same? Okay, I'm going to walk you through that today. And from there, I'm also going to go to a situation where we got multiple vector means, and we want to want to construct confidence interval on that testing hypothesis. But before we actually going to go into what would be the appropriate test statistic or confidence interval formula to use when the variances, the covariances are not the same, we need to first investigate, whether the two groups that we are comparing have the same covariances. So I present to you T-square test, okay, with heterogeneous covariances. Okay, so before you actually going to see how the T-square test is going to be or the confidence interval is going to be, I need to first walk you through how do we test whether the covariance of the two groups we want to compare is the same or not. Okay, so I'm actually going to walk you through that. Now, let me say this. If you want to test for equality of the variances, we have a kind of, we use a test that we call box M test. Give me 1 second. I think I'm going to for show you, I'll show you that. Okay, I'm going to show you the code to go about testing whether two covariances are the same or not. But let me just assume here, let's assume that the covariances are not the same. Okay? I'm still going to show you the test, how to investigate whether covariances are the same or not. But let's say we've conducted the test and the covariances are not the same. If the covariances are not the same, then what we did on Wednesday is not going to be appropriate. Because Wednesday, we assume equality of covariances and we use the idea of a pooled covariance. We pooled. We normally pooled covariances when it is assumed that they are the same. But when they are not the same, okay, then we do not need to pool. Then we're going to have a different test statistic, which is what I'm showing now. Okay, you can see there's no pool here. If you take a look at what I have, what I'm showing now, you're actually going to see that we're using, if you take a look at this, X1, covariance, the sample covariance of the first group and the sample covariance for the second group. Can you see that? So here we did not put the covariance. Why? Because we are assuming, or we've conducted a test, that the covariances between the two groups are not the same. When they are not the same, we're not going to put. We're going to make use of that guy as a t-squared. When they are the same, we're going to put. Now, we're also going to consider different kind of scenarios. At times, we could be working with a large samples. At times, it could be a small sample. Okay, so how is the t-square formula going to be, okay, when the covariances are not the same? Okay, whether for large sample, we did it the other time. I call one finite and asymptotic. Okay, the finite and asymptotic. So it's synonymous with large and small sample here. So, and look at what I'm trying to say, here is that the probability, the moment, if the minimum of N1 and N2 minus P is large, we can use chi-square approximation. It's going to be the distribution. Okay, and in a situation where the minimum of N1, N2 minus P is small, we can assume normality, and the t-squared will follow that. You can see that? T-squared is going to follow that. Otherwise, t-squared is going to follow chi-square the moment the minimum of N1, N2 minus P is large. For small, it is like that. So just wanted to take note of that. Now, you can see here, you have a V and P. Of course, you know what P means. P is the numbers of variables. V here is this guy. Okay, you need to compute that guy for V. There's a lot to do in that expression. Okay, SK, you can see SK. You're going to have S1, S2. Don't forget you are summing. K start from 1 to 2. So take a look at that. And what is SO? What is XO? This is XO. Can you see XO? SO is like combining X1 and S2, the sample covariance for the first and the sample covariance for the second. So take a look at that. Now, with all this formula, we actually have a way, we have a coding out, okay, that we're actually going to show, okay, a simple coding out. Now, I need you to pay attention. The very first code is alternative squared when we are assuming equality of variance, or equality of covariance, similar to the one we did on Wednesday. Okay, now so this is a real life example. Take a look at the real life example. The real life examples here, I have, MPG, the DISP, the HP, WT. I'm comparing that for two type of group. What distinguish between the group is cylinder 4 and cylinder 6. Okay, cylinder 4 and cylinder 6. And variance equal means equality of covariance. When there's equality of covariance, now if you take a look at the result here, please pay attention. I need you to pay attention. The result here is you can see asymptotic, variance equal true. Okay, and here asymptotic false, variance equal false. Please pay attention. I want to explain the two. This is the two is not for large sample. That is why you can say asymptotic false. When asymptotic is false, it means we're talking about finite or small samples. But the two, we're assuming equality of covariances. That's why you see variance equal true. Does that make sense? Okay. Now, that is using a real life data set. And of course, you can also use a simulated. Okay. You can also use a simulated data set. Take a look at what I have, simulated data set. Okay. 4 variables. F, that is why you say 4. N equal to 100. Okay, X, Y is to indicate we got 2 different groups. Does that make sense? It's like simulating for 2 different groups. Each of them follow normal distribution. Take a look at that. And of course, if you pay attention to what I'm actually doing, if you take a look at this, asymptotic false, variance equal true. Asymptotic false, variance equal false. You know, if you take a look at it too, okay, I'm not also talking about large sample. I'm talking about finite or small sample. That's why you see asymptotic false. But I'm still assuming that the covariances of the 2 groups are the same. Does that make sense? Okay, so I just wanted to take note of that. Now, to finish this material, I want to introduce you to multivariate analysis of variance. You know, the one we've completed now is when we are only comparing 2 groups. But right now, we want to go into more than 2 groups, multiple groups. Okay, now before I'm actually going to show this, what I'm going to do is, before I'm going to go into formula, because what we're going to do again, I'm actually going to start from univariate analysis of variance, or then I will extend that to multivariate. And of course, that is what we've been doing. We've been starting from the univariate. From univariate, we go to multivariate. But you know what? I'll first give you our intention. I'm going to do a lot of stuff on the board before coming here, so that the moment I give you the intention, our intention on the board, then we're going to come back here. I'm only going to show you the formula. Okay, so I need you to pay attention. Okay, I need you to pay attention. Now, if I want to talk, I want to talk about inference on multiple vector means. Okay, inference on multiple, okay, vector means. I want to conduct a statistical inference on multiple vector means. Okay, when I say statistical inference, I actually means I want to test hypothesis. I also want to construct a confidence interval. And you know, if I have more than 2 groups, if I want to compare means in more than 2 groups for univariate, where I only have 1 variable, okay, just 1 dependent variable, okay, we actually normally talk about ANOVA, okay, with a risk analysis of variance. Analysis of variance divided into, we can do 1-way, we can do 2-way, we can do 3-way and factorial design and so on like that. Okay, so now in the univariate setting, okay, maybe what I only want to compare groups. Okay, I want to see whether a particular dependent variable is the same in all groups. Okay, so we do that. So we have 1-way, we have a 2-way analysis. 1-way is when I have one factor. Okay, one categorical factor, and 2-way is when I have two categorical factors. Okay, but this is going to be just, here the one dependent variable. Okay, it's going to be just one dependent variable. Okay, but what if in a situation, what could lead us, into considering multivariate analysis of variance? I'm going to give you an example now, and I need you to pay attention. Okay, now I'm going to give a scenario in earth science, where a researcher is interested in investigating effect of drug S and drug Y, okay, on some selected X metric outcome. Now, maybe the selected outcome is number 1, blood pressure, number 2, cholesterol level, and number 3, heart rate. Please pay attention. If you take a look at this, okay, this researcher is interested in investigating the effect of drug S and drug Y on some. Now, the drug S and drug Y is actually, they want to test that on patient, maybe patient that's having a disease called hypertension. Okay, hypertension. Okay, that is the disease, and they want to see, okay, how we want to see whether the blood pressure is going to be statistically significant different in drug S and drug Y. Not only that, the cholesterol level, not only that, the heart rate. Okay, now if I want to pursue this, okay, the independent variable here, okay, is drug S and drug Y. This is the factor. Okay, we only have one factor with 2 levels, drug S, drug Y, and the dependent variables that we have here, blood pressure, cholesterol level, and heart rate, makes that to be multivariate. Does that make sense? Now, why is it that I cannot just conduct univariate ANOVA? Why is it that I cannot conduct univariate ANOVA one at a time? Why is it that I cannot look at the effect of the drug on blood pressure using one-way ANOVA? Why is it I cannot use conventional univariate one-way ANOVA to measure the effect of the drug on cholesterol level separately? Why is it I cannot use univariate ANOVA to measure the effect of the drug on the heart rate? The reason why I cannot do that is because I'm actually, when you have a multiple test, okay, the type 1 error rate will be exceeded. The probability of making incorrect conclusion will increase. That is number 1. Number 2, okay, that approach, conventional one-way, univariate approach, will ignore correlations among the dependent variables, because there could be correlation between blood pressure, cholesterol level, and the heart rate, and that will ignore that. And when it's ignored that, then it means we are not necessarily going to have, it's not going to have a huge statistical power. Does that make sense? So the idea of using a multivariate analysis of variance, because we are able to control the type 1 error rate. Number 2 is able to adjust, to put into consideration the correlation among the dependent variables, and not only that, it will enable us to detect multivariate effect, and thereby, we're also there's going to be a kind of gain in statistical power, and that is why we're going to make use of, multivariate analysis of variance here. I'm going to give another example now. I've just given an example in earth science. Now, another example that I'm actually going to give is, a researcher may be interested in investigating effects of teaching methods. When I talk about teaching method, okay, the traditional one like the one we're having now, in person, okay, the traditional, I'm talking about teaching delivery, okay, online, and hybrid. Okay, hybrid is, maybe at times we do online, at times we do in person. Okay, now I want to look at the effect of this on performance, on not just performance, academic performance of students in various subjects, of academic performances, performances of students, okay, in various subjects. Maybe the subjects like maths, science, okay, and English, maybe reading or something. Take a look at that. Now, the one factor here, this is the factor with 3 levels, okay? And how many, of course, we have so many, dependent variables here. The idea of multivariate analysis of variance is also going to be used here. And this is going to be, because we got one factor, okay? We got one factor, okay? It's going to be one-way multivariate analysis of variance. Now, finally, before I start showing, I'm going to give you example for two-way multivariate. I'm trying to give you like what, illustrative example before I start showing some, formulas and so on like that. You're only going to understand the essence of formula if you understand our intention. That's why I'm trying to show all this. Now, this can be achieved using one-way maneuver. We call that maneuver, multivariate analysis of variance. Now, I want to give example for two-way now, two-way maneuver. So when I say two-way maneuver, I'm actually going to have more than one factor. Okay, that's what's going to make a difference. Now, I want to look at the effect of gender, okay, effect of gender and extracurriculum activity, extracurriculum activities, maybe the kind of group students belong. Okay, some are into sports, some are into debate, and probably music. Okay, and for gender, male, female. Okay, now I want to look at that on the academic performance in various subjects. Okay, maybe I'm still referring to this subject here, but this time around, I'm looking at the effect of gender. I want to see whether the performance in English is going to be the same, okay, between the level of gender. I want to see if the performance in in maths, okay, in each of these, is it going to be the same in this level? I also want to see whether it's going to be the same in the group they belong. Because of that, this is going to be the first factor, it's going to be the second factor. And the moment I have two factors, then I'm also going to consider interaction. Okay, there's going to be possibility of having interaction between factors. Okay, and what I'm going to, so interaction between factor is that I'm actually going to have a situation where I have gender multiplied by extracurriculum. Okay, gender multiplied by that. What is it meaning? It means the behavior, if when interaction is significant, what it means is that if I want to measure the effect of gender on the response, that depends on the extracurriculum activity. So which means a particular factor is not consistent. The behavior of if a particular factor is not consistent, which means it depends. When the effect of a factor on the response depend on another factor, then we need interaction. Now, like I said, I've given you intention now. Now, after you understand this intention, okay, I'm going to show you what are the test statistics that we're actually going to use. There are different kind of test statistics that we're going to use, okay? Then after that, what are the steps if I want to conduct, this. Now, let me quickly tell you the step before I'm going to show you formula. If let's say for instance, I want to test this. I want to test this, testing this, we can use, there are different kind of, tests. There's something that we call, number one, we have weak lambda, okay, statistic. Okay, we have pillar trace. We have Otelline trace, and we have Roy's. We have Roy's largest roots. Now we can use any of this, but what I'm going to show you in the literature, what I'm going to show you today, is what I've prepared is weak lambda. Weak lambda is very, very popular, but we also have other. Now, if I conduct for one way a multivariate analysis of variance, if I use any of this and it is significant, let's say the p-value, some of you may be wondering, since we have so many dependent variables, do we have one p-value or several p-values? It is one p-value. Does that make sense? We call it global p-value. Now, when that let's say p-value is significant, I'm assuming if p-value is significant, in step 1, you conduct any of these tests. If p-value is significant, then in step 2, you need to go back to univariate ANOVA. Does that make sense? I'm going to say that again. Let's say I'm conducting this and p-value is significant. You know what I'm going to do? Now, what I'm going to do is to go back to univariate ANOVA, where I'm going to consider effect of teaching method on maths only, or effect of teaching method on science only, effect of teaching method on English. But if the p-value is not significant, I don't need a separate ANOVA. I need a separate univariate ANOVA if the p-value is significant. Does that make sense? Now, because why do I need a separate ANOVA? Because the p-value that we have in the multivariate test it's not going to tell us which of that is significant, because you have a global p-value. Does that make sense? You have a global p-value. So for you to be able to know which of the subject is significant, and that will necessitate, conducting a separate univariate ANOVA. And the moment you conduct a separate univariate ANOVA, how many p-values are you going to have now? 3 p-values, because you do separate. Okay, that is step 2. Now, there's possibility. This may be significant. That may be significant. This may not be significant. If any of that is significant, then step 3 is to conduct what I call a post hoc test. Post hoc test. Post hoc test that we call multiple comparison test. The multiple comparison test just to figure out where the difference lies, okay, in the group. And we have different kind of multiple comparison tests that we can conduct. We have a Turkey, we have a Bufferoni, we have a Skefi test, and we have a game almost test. Okay, I'm actually going to walk you through all of that. Now, I want to go back now to the material. Now, you're going to have opportunity now. Okay, now you understand our intention. Okay, if you take a look at this material now, what this guy is telling you that, okay, in the one-way ANOVA, conventional univariate, this is what we have, okay, and this is the model. This is one-way ANOVA model. Okay, the mean, the treatment effect, and the error. Take a look at that. And we have assumptions. Error follow normal distribution with mean of 0 or sigma squared. And the constraint is that the summation of nk alpha k has to be 0. Don't forget, the alpha k here is a treatment effect. Okay, the treatment effect. Now, that is for the univariate. Now, in the univariate ANOVA, we just want to tell you how do you find the sample mean, how do you find the treatment effect, how do you estimate the error, okay, and so on like that. How do you find this, the overall mean? How do you find the group mean? You've done that in univariate. And of course, in univariate, you know that we are actually decomposing the sum of square total. You know, the idea in analysis of variance is that we want to break down, we want to split the total sources of variation into components. The SS total means total sources of variation into two components. Now, because I'm dealing with one way ANOVA, it's going to be two components. One will be variation within. Okay, this is variation within, this variation between. SS between means variation between the levels of the categorical factor, okay, the variation between groups. But this guy is saying variation within a particular group. That's what this guy is trying to say. Now, from there, we have F. We use F test in the conventional univariate analysis of variance one way, and we take a decision rejecting H naught if the test statistic value is greater than what you check from the table. Okay, that is for the one way and univariate. If I want to extend that to multivariate, okay, I needed to take a look at the model that we have. The model still stay the same, except that I'm going to show you something now. You can see alpha k EKI. If you want to go back, you see the same SKI, but except that the other one is going to be a vector here. This model here is going to be a vector. Okay, so we're taking a look at this now, and so when we talk about absorption now, we're not going to say error follow normal with just 0 and sigma square, but here in the multivariate case, it's going to be error follow normal distribution. You can see that 0p means the numbers of zeros we're going to have depend on the numbers of variables. And of course, instead of just sigma square, we're going to have a covariance. Can you see that? And so now we're now extending now to multivariate case. Now, we also need the composition. You remember I showed you the other time in the univariate case where we partition, where we partition, the sum of square variation into various components. We're also doing that in the multivariate case. But in the multivariate case, we call that sum of square product. Okay, sum of square product total, decomposing sum of square product total. We are decomposing that to sum of square total, sum of square between and sum of square within. Okay, just like what I just showed you right now. So if you take a look at that, okay, we are applying, analysis of variance in multivariate way. Now, I needed to pay attention. Okay, now if I want to talk about this guy, that is sum of square product within sum of square product between sum of square product total. The sum of square total, sum of square product total is the total source of variation. We're splitting that into two components, into the one that can be explained and the one that cannot be explained. The one that can be explained is between. The one that cannot be explained is within. Okay, let me tell you this. We're interested in within. Take a look at this. The whole of this guy, we can use W to represent that. It's going to be a matrix. In a one-way analysis of variance for univariate case, that is not a matrix, that was a scalar. But right now, each of these is going to be a matrix. Now, the W now, we want it to represent the multivariate. Can you see that? I mean, to represent the sum of square within this guy here. Okay? Now, this guy here can also be written as this. Please pay attention. Okay, if I want to, I can use that or use that. It's the same. Okay, the two of them are the same. What is SK? SK is the sample covariance for a particular group, maybe for group K, when K equal to 1, for group 1, for K equal to 2, for group 2. Don't forget, we're going to have different covariance for each group, right? Then NK will be the number of observation in each group. Does that make sense? Okay, how do you get your SK? Don't forget, getting your SK is sample covariance, reminding you of what we've done before. That's how to get that. Okay, now please pay attention. I want to set up my one-way multivariance, multivariate analysis of variance table, just like, that is similar to one-way analysis of variance table in a univariate version, and I need you to pay attention. If you take a look at the decomposition that we've done the other time, okay, we need B. B is going to serve as the variation between. We're going to represent that as matrix B. The variation within, we're going to represent that as matrix W. Okay, then the total variation is just going to be the addition of the two, right? Okay, all of them, they're going to be matrix in matrix form. Does that make sense? And they're also going to have their corresponding degree of freedom. Okay, for between, it's going to be the numbers of groups minus 1, and so on like that. Okay, I want to move right now. Any question on this table? Is there any question? Okay, now, I want to set up a wiki lambda. I told you the other time, we got, 4 different ways to look at this. We can use a wiki lambda. We can use a pillar trace. We can use a lean trace. We can also use a Roy largest root. But what I prepare now, let you know, is wiki lambda. The wiki lambda test statistic is actually this. Do you see that? And before, of course, if you obtain your W and B, right, you can, and I told you they are matrices on their own. You find the determinant of W. You add matrix B to W. Don't forget, that was the reason why when we started initially in the early, when we started in the early semester, we were adding matrices together, we were multiplying matrices. Now we want to make use of that now. Without matrix algebra, the knowledge of matrix algebra, there's going to be difficulty moving forward. So right now, you see the way I set up my wiki lambda. My wiki lambda statistic is just going to be the ratio of determinant of W, which is within variation to the total variation, because the total variation, B plus W. Does that make sense? Fine. And what we're testing is the hypothesis. So we call that wiki lambda. Now, when do we reject H0? Please pay attention. We reject H0 if we have a smaller value of a wiki lambda. What will make us to have a smaller value, I said if that is smaller than the expected under the non-hypothesis. The smaller value of wiki lambda, we can only have a smaller value of wiki lambda if the denominator, that total denominator, is bigger. Does that make sense? Because when you have a fraction, when the denominator of a fraction is big, the fraction is going to be small. Does that make sense? So take a look at that. Now, but this is where I want you to pay attention now. Okay? We can use different distribution to take a decision regarding the wiki lambda depending on the numbers of groups you want to compare and the number of variables. When variable equal to 1, when variable equal to 1, okay, variable equal to 1 is just conventional univariate ANOVA, and the group is 2 or more, okay, we need to recompute. Please pay attention. After obtaining your wiki lambda, you need to get a new statistic. You see the wiki lambda in that? G is a number of groups you are comparing, N is the number of observation, and that will follow F distribution. F distribution with two different degree of freedom, G minus 1 and N minus G. Take a look at that. Okay, if you want to take a decision now, rejecting the non-hypothesis is when that guy that I actually highlighted now is greater than F that you check from the table. But what if in a situation where there are two variables involved? Okay, two variables involved means bivariate. Two variables involved, okay, P equal to 2. Two variables involved, and the numbers of group is 2 or more. Okay, this is going to be the new test statistic. Don't forget, this is after you have computed wiki lambda, which is a ratio of sum of square products within divided by the total. You find the determinant of that, each of that. So then that's also going to follow F distribution. Following F distribution, you have a different degree of freedom now compared to the first one. Now, situation where P is greater or equal to 1, and you only have two groups. Okay, you only have two groups. Okay, that's what you're going to have, and that will still follow F distribution. Now, in each of these, they all follow F distribution. They have different test statistic, which is a function of wiki lambda. They follow F distribution, but with different degree of freedom. Does that make sense? Is there any question here? Is there any question? Okay, now I'm actually going to move right now. Okay, now what if in a situation where N is large? If the number of observation is large and H naught is true, then we're actually going to have a different test statistic in terms of wiki lambda. Can you see wiki lambda again? The wiki lambda, the lambda star. Okay, and we want to take a decision now. We're going to check from a chi-square table. When that guy is greater than the chi-square, we're actually going to reject. Okay, so we have other one-way maneuver, like I told you the other time, apart from wiki. We have Otterlin trace. Okay, Otterlin trace, that's how to get it. If you take a look at the Otterlin trace, pillar trace, Roy largest root, okay, all of them depend on B and W, which is sum of square product between and sum of square product within. Let's take a look at all of that. Okay, but let me tell you this, it is actually discovered that pillar trace is more robust to non-normality, because one of the assertions of multivariate analysis of variance is normality. What if in a situation where there's a violation of normality assumption, using a wiki lambda may not make sense? And that's why, pillar trace actually more robust in that regard. I quickly want to move. Now, this is a coding R. Don't be scared about formula. This is a coding R. Now, when you take a look at this coding R, okay, actually having MPG, DIS, PHP, WT, okay, see the way it is written, you know what I did? Oh my God, what I did. I conduct different kind of tests. The first one I did was a pillar test, using a pillar test statistic, okay. The second one that I did is using Wix cylinder. Can you see that? The third one that I did, okay, so I also did the one with the Roy test. I told you there are different kind of tests, and it's like they are taking the same decision because the p-value is small in each of that. Take a look at that. Okay, so that's how to do that. And now the Otterlin, look at the Otterlin too. So the 4 different tests here, I conducted that, and you can see the p-value. I told you, you're only going to have just one p-value that we call a global p-value, and the moment p-value is significant, then you will need to return. Your step 2 is to return to separate ANOVA. One where you do univariate ANOVA, where you investigate the effect of the factor on the dependent variable one at a time. Does that make sense? That is when the p-value is significant. Now, I think I'm done with one way. That I'll quickly move to multi. Now, the interval, for that, Befferoni and the like, is actually there. There are different kinds of intervals that, the multiple comparison tests that you can use, where you can use a Turkey HSD, you can use Bonferroni, you can use Skefi. Now, when do we? Okay, I think I'm going to spend. I'm going to do this now. If you have rejected the null hypothesis, whether using Wikilanda and the other, and you resolve into univariate one way and over, okay, and you realize that one of that is significant, the next step, you want to conduct a multiple comparison test. What determine the choice of multiple comparison test? Now, let me tell you this. We got four. When I say multiple comparison test, we normally use that when the non-hypothesis